So without further ado, John Ensworth, who's going to talk a lot about nothing.
A lot about it. Thank you. And we're setting up some shorter chairs here, so we can get some kids forward. We can also free up some seats for the people in the back. So if you want to just take a moment, kids can move up here.
Good evening.
You guys get the front rows.
Yeah, front row. I bite though, you gotta watch out.
He kicks more than he bites.
I kick and bite, yes I do. All right, well, welcome everyone. Thank you very much for coming tonight. So, yep, a talk about nothing. So let's introduce you to, let's see if it clicks. It's not on. We're going to introduce space.
Yay!
That's it. All right, any questions? Okay, you got a question.
Are we going to see the moon and stuff?
Not the moon, but you will see other things after the talk part. Yep. All right, you can bring it up.
Oh.
All right, another version of nothing is a show about nothing. So, all right. So, do you guys like astronomy? Yes. All right. You like something that's mostly nothing. So, all right. I know. It really is. I'm going to show you how much nothing there is. But you're not much yourself because every atom that makes you up has a little nucleus in the center. It's about the size of a seed from a grape or an apple on the 50-yard line of an entire stadium where all these electrons are going around. And their points, they don't really have any size. So you're a bunch of emptiness too. Or at least the politicians that we know are. If you got the entire human race and squeezed all the space out of all their atoms, they would fit inside of a single sugar cube that would weigh 50 million tons. So it's time to lose some weight. So, all right. And this atom these atoms are made of are 10,000 times emptier than the solar system, but the solar system is still really empty too. As we go up in scale, you find there's just huge amounts of nothing between everything. So a lot of stuff going on the Earth. That's a big old rock. But go up to the solar system and you have now light hours between little specks of dust that are planets and rocks and one little star in the middle. Even if you go in the asteroid belt, you know, in the movies, you go and there's all these rocks tumbling around the asteroid belt and you got to zoom the Millennium Falcon around it. And if you were actually in our asteroid belt standing on one of those asteroids, you looked around, you probably wouldn't see another rock. Not easily. Not nearby. You need a telescope or binoculars. It's not that full of stuff. Go up to the interstellar neighborhood. So you got the nearest 20, 30 stars or so. They're on average about 10 light years apart. 10 light years of nothingness between them. Go up to the Milky Way. Oh, that looks like there's a lot of stuff there. Again, lots of stars, about 150,000 light years across. You've got them all about 10 light years apart. In somewhere around 4 billion years, don't panic, the Andromeda Galaxy is coming to crash into us. Big collision. Should be in the news soon. It'll make some combined galaxy in the end that some astronomers want to call Milkomedia, but I think we should probably let civilization 1 billion years from now decide what to call it. But when they collide, they're going to pass through each other, and the chance of any two stars hitting is almost zero. Better go play the lottery than hope those two stars collide. So that's a lot of nothing. It's a big fluff ball. Go out to our local galactic group. Now you've got millions of light years between things, millions of light years of nothing. Go up to the supercluster of galaxies. You have huge voids that are showing up. They're huge expanses, tens of millions of light years across of nothing. Local supercluster up to the universe, you're up to billions of light years with just little specks of glowing material and all sorts of nothing in between. So hopefully you don't feel too small. Yes?
So what's your point?
There's nothing out there. let's go back to early ideas. What has humanity thought about nothing? Well, ancient Greeks said you really can't have nothing. That would be like singing and not singing at the same time, or walking and not walking at the same time. They said it just didn't logically make sense to have nothing. So they dismissed the idea. Ancient times, the church didn't like the idea of nothing, since God's everywhere, so there's something around, right? Also, if nothing exists, you're getting very close to letting the people touch the idea of zero. And zero, I've said this in earlier talks, is a dangerous concept. All right, so I've done this before. What's 0 divided by 5? How many 5s go into 0? 0, okay. That's easy. Yep, 0. All right, let's flip it upside down. 5 divided by 0. How many zeros fit inside of 5?
All of them.
All of them, thank you. Best answer. Well, you have to create the idea of infinity then. You have to start, an infinite number of zeros have to fill up a 5, and it gets really weird. Something called calculus got invented to kind of help us work with that. But it was better just not let people deal with zero. So, by the 18th and 19th century, we started to figure out light. We started to do little experiments with prisms and slits and clever stuff like that. And we saw that light was made of waves. Well, if you're going to have a wave, then you've got to have waves traveling in something. It doesn't make sense. Nothing can be waving. So for years, nothing was not possible. How many double negatives can one talk have? So we had ideas like the plenum and then the aether, or ether. We get the word Ethernet from this. Little cables that go around and connect your computers in your home. I don't know why the cables are called Ethernet when Wi-Fi would be more of an idea of something that you don't see that's everywhere that lets you work with the internet. But anyways, I guess I didn't think that was coming. So the plenum is the idea that all space is filled with matter. And you get the very famous term, nature abhors a vacuum, from that. So the belief was, well, yes, there had to be something throughout all the universe, probably air. Well, then people started climbing mountains. Well, oh boy, there's less air up here. Then the hot air balloon came along, and people almost died going up to high altitude and not being able to breathe. So something started to creep into humanity's consciousness that up at the top there may not be any air. So the ether comes along. We're going to do away with air. We're going to let some mysterious fifth element. We've got fire, water, air, earth. We'll add this ether or aether to it. And this is, it translates to pure air or fresh air or void. That's kind of a weird use. But we'll fill the universe with this ether, and that will be what waves will be able to ride on, and everybody's happy. Everybody goes home just fine. Well, of course, the ether died in the late 1800s, the end of the 19th century with the Michelson-Morley experiment. And what they figured out was, well, you got ether out there. If I'm sitting here still, I don't feel the air in this room at all. But if I start moving, I get a little breeze in my face. All right, so we know the Earth is going around the sun. Well, there should be some breeze in the ether that's blowing through. And probably the sun is moving, and so that would make an overall breeze through the solar system. So let's experiment with this. Light is using the ether to travel through space, then we can measure this. So they set up a neat little experiment before lasers like my pointer. They would have loved to have a laser. We do this experiment in basic physics labs in high schools and college using lasers, pointer lasers and like that. You break the light apart, you bounce it off two mirrors, and you bring it back together, and the light interferes with itself and makes this really neat little colorful pattern called an interference pattern. And if the path distance between the mirrors here and the mirrors here change even a tiny bit, you'll see these colors shift. It's very sensitive to this distance. Or, if the distance doesn't change, if the speed that the light is going because of this blowing ether coming through my experiment changes how fast the light's getting through, you're going to see that little shift in the interference pattern. It's a very good way to measure it. They tried morning and night. They tried beginning and the end of the month, one time of the year, the next time of the year. They tried changing the orientation of their experiment. Nothing mattered. The fringes here never changed. So the ether doesn't exist. And Einstein needed that because he then built upon that all of special and general relativity. And he was able to show that light waves can go through a vacuum naturally. Mathematics that existed at the time said it could, but no one really had that down yet. So answered another problem, that if you had an ether, that maybe the planets would eventually slow down as they push against this ether, and they weren't doing that either. But there was a fly in the ointment from way far back in 1644. We have the invention of the barometer by this Evangelista Torricelli. Did I say it right? I don't know, I tried. Torricelli, thank you. Sounds like something I would have had for dinner tonight. And put a little tube full of mercury in, turned it upside down real quick into a bowl of mercury, and the mercury drops down to a certain point, about 30 inches up, and it leaves a vacuum behind. So first thought was, wow, this vacuum can do work. It's holding up the mercury. It really isn't. The atmospheric pressure is pushing down here and pushing the mercury up to the level where the weight of the mercury inside equals the weight of the atmosphere. So as storm systems come and high pressure systems come, this will go up and down and tell you what the weather is. He set up, I read a water barometer in one town, and when it went down, it would storm. We know that. Pressure's falling, here comes the storm. The townspeople made him tear it down because they thought that it going down made the storm come. So I'm going backwards there. So, but there is a really good concept of a vacuum up in this little top part of the chamber. There is a lot of stuff in there though. Mercury does evaporate, so there's a lot of mercury vapor in there. The longer that you go, the more it gets some vapor in there. There's probably a little bit of material, the glass or the tube that's dissolving out. Maybe there's some water that we got left in there. So it's not a really good vacuum. What can we do to get a real good vacuum? We can go to space. Space between the stars, there is stuff. There's a little bit of hydrogen, some helium, some atoms, protons, electrons zipping around like that. Between the stars, there's about one particle for every cubic centimeter, a little bit bigger than a sugar cube, or a little smaller than a sugar cube. One particle. Go out between the galaxies here, you're now to less than one per cubic centimeter. Close to home, we have a lot of stuff coming from the sun, a lot of atoms and charged particles streaming out on the solar wind. This contributes to aurora, combined with our magnetic field and our atmosphere. But this is heading out into space, creates a bubble around the solar system, the solar environment. And inside of this bubble, it's not as good of a vacuum. You're up to about 5 atoms per every little cubic centimeter. It's enough to push comet tails away from the sun no matter where the comet is moving. So as comets come into the sun, tails behind them, that'll make sense because it's behind the comet. But as the comet whips around the sun and then heads out again, it's actually heading into its own tail. That's because of the solar wind. This 5 atoms or so per cubic centimeter is enough to push the tail around. This outer shock or boundary also helps us protects us from cosmic rays, some of the high energy ones coming from intergalactic and galactic sources of violence. It's kind of nice. Let's go to someplace really dusty and cloudy, like the Orion Nebula. Everybody loves this. We're coming into winter. go out late at night. Actually, my favorite thing is at midnight on Halloween, you go out and look east, you'll see Orion rising. So that's my internal reassurance that winter is coming. So you got 10 atoms per cubic centimeter in this big, cloudy, colorful thing. That's still pretty close to a fantastic vacuum. It's still much better than the one in his barometer. But it's not just atoms and particles that are floating out in space. We have other little particles that come from the subatomic world, and these are called neutrinos. Almost massless, traveling almost at the speed of light. You are getting 65 billion for every little cubic centimeter. Taking the average volume of you guys, that's about 100,000 million, billion, trillion, quadrillion. 4 quadrillion are going through you right now every second. But they're so light that over your lifetime, only about 1/10 of a gram of neutrino mass will have pushed against you. That's about 1/10 of a paper clip. So that's not going to push you around much. So, but that's a lot of these little particles. But there's other particles out there, or energy sources, dark matter and dark energy. These are placeholder names for these phenomena because we just don't know what they are yet. They will get better names someday. If I discovered it, maybe it'd be the Ensworth particle. That'd be nice. All right, that's not happening. The current numbers are that about, oh, the yellow is not easy to read, 4.9% of the stuff, energy budget in the universe is ordinary matter. So this stuff and electrons and like that. Dark matter, we'll talk about what it is in a moment, 26.8%, and dark energy, 68.3%. Now this is an update number. You may have heard more than a year or two ago numbers more like this. The Planck mission looking at the background glow of the Big Bang, the cosmic microwave background radiation, tweaked those numbers a little better. But this is embarrassing when you're an astronomer and you can only really tell people about 5% of the universe. But it's also a lot of job opportunities right there. So,
so when you define dark matter and dark energy, what are we? Is that an unknown? What is that?
I'll get into that right now. Thank you for asking. There's a video for playing if we got John back there. So dark matter was suggested back in the 20s and 30s. Vera Rubin, Kent Ford came up with some really good measurements that really solidified the need for dark matter existence. When you look at a galaxy like pictured here, let's say that's our galaxy right there, the size of the dark matter cloud around us is tremendous, 10 times the size of the galaxy. And the reason we think it's there is because stars out in the edges of the galaxy should be going a lot slower. Kepler told us that. But they aren't. Towards the black hole in the middle, I'll go to the next slide here. Thank you, John. Things rotate like that, fast towards the black hole, a little slower, and then they all kind of go at the same speed all the way out to the edge. So something out here is rotating and dragging it all along. It's this dark matter cloud. And that was pretty convincing, but now we can look at distant galaxies and see how their light gets warped through invisible clouds of dark matter in between us and them. And we can look at the cosmic microwave background radiation glow and look at how it appears, and I don't want to go any deeper in that. And we can get an idea of where these clouds of dark matter are. Here's a big cluster of galaxies. And looking at how the light is bent, a computer can give us a blue overlay that shows us where dark matter is in this picture between us and there. Here's a very famous example called the bullet cluster. These are two clusters of galaxies that have passed through each other. Their dark matter is in blue, and it keeps on going. It doesn't care about this big collision that's just happened, but the gas and dust in the two clusters have bothered each other and have slowed each other down and have gotten really energized by that and are giving off gamma rays. So that's what the pinks are right there. So we can see some dark matter there. Again, this takes computer processing and special effects to see it. We're not seeing it directly. These are almost artist renditions based on real data. So what could these things be? Well, the favorite right now theory is or called WHIMPs. That's kind of insulting. Weakly interacting massive particles. Okay, so you got WHIMPs and weak together. So now they're really driving it home. There's something wimpy weak going on. But really, this is the weak nuclear force. 4 forces that we have: electromagnetism, gravity, and then the weak and the strong nuclear force. So the idea is that all particles interact with these forces to various amounts. Some only see one. Some interact with maybe all 4 forces. A neutron is neutral, so it doesn't care about the electromagnetic force. So it doesn't play with that force. These little particles, if they exist, would primarily only interact with the world through the weak force. And so we have set up experiments to look for these interacting in big tanks of cleaning fluid and tanks of water. And so far, we're not finding anything. And we've set up some really precise experiments. The articles are now coming out in the journals that are saying that the dark matter astronomers are getting concerned that all the regions that it could be are being explored and nothing's being found, and we're shrinking down into one little area of energies and phenomena that could be left, and then this WHIMP idea is going to have to go. And a top contender is not waiting in the wings. Some people do really like what's called MOND. This is a modified MO, Newtonian dynamics. And this says, quit looking for particles, don't look for things like that. All we don't understand is how gravity actually works. So on big distances and across big amounts of empty space, we just have to have a different equation to tell us how gravity works. But there's problems, big problems there too, in the modified Newtonian dynamic side. And other people are striking out going, okay, well, if these guys all fail, then we better come up with other types of gravity and like that to solve it. We just don't know though. That's about as far as I can drive you into the dark matter direction. 26.8% mystery out there in nothingness.
Does that mean that that 26.8% isn't accounted for?
We can weigh it. We can weigh it. We just don't know what it is. Yeah.
Okay.
Yep.
A couple of years ago, the Einstein telescope, there was an excellent article on all of this.
Yep.
Really did a good job. But a couple of years ago? Yeah.
The biggest chunk, though, is dark energy. This was discovered much more recently by 2 teams, one in 98, one announcing in 99. We had Nobel Prizes to these 3 folks. And we have now looked at the cosmic microwave background radiation appearance, gravitational lensing again. We've looked at the light curves of supernova, and the large-scale structure of the universe is all supporting that there's this dark energy phenomena going on, but it's even more mysterious, I think, than the dark matter candidates. And basically, this is something that's beginning to accelerate the universe. The tipping point between gravity pulling in, dark matter and normal matter pulling everything together, was about halfway back in the universe. So about 7 billion years old. We're at about 13.5 billion years. And since then, dark energy has begun to really take over and start to accelerate the expansion in the universe that we already see. How much that's going to go, and whether the universe gets to the point that it expands so rapidly that galaxies are pulled apart, and then individual star systems are pulled apart, and then solar systems are pulled apart, and then planets are pulled apart, molecules are pulled apart by dark energy or not, we don't know. Probably not. That's pretty awful. But that's called the Big Rip, and that's one way to end the universe. The 2 top candidates are a cosmological constant, and something called a scalar field. And the difference between these is a cosmological constant is constant. It never changes. Every single point in space always had and always will have the same amount of dark energy. In the early universe, gravity was just able to hide it. In the present day, gravity is losing its grip and the expansion is starting to speed up. More complex is something, a scalar field, where over space and time in different regions of the universe, it can look, it's a different expansion. So it's an expansion rate that changes. And it can look like a cosmological constant if these changes are slow, but nobody really has a good grip on these two yet. But it makes up the nothingness that's out there. And it's making more nothing all the time. So, sort of embarrassing to have all this unknown stuff, but really it does mean lots of excitement in the future. We still have our telescopes to look at this stuff here, from radio up to gamma rays. But let's go beyond all this energy stuff, and this matter stuff. Let's look at particles and fields. Now, I've talked about this in earlier talks, that nothing around you really is real. This sounds like solid stuff, but it isn't. E equals mc squared says energy and matter are interchangeable. Matter is solidified energy. You go down to the atom scale, you go below an atom, it's just fuzzy stuff. Particles and waves are interchangeable. People even had the idea of wavicle to try to explain it, but that didn't really work well. But another approach to this is called quantum field theory. So instead of dealing with little balls of matter and particles rolling around, we're going to deal with something called fields. And so if we excite the field, we get a particle. So let's say the carpet in here is a audience field. Okay, now before you guys came here, there were chairs and a big flat carpet. That's an unexcited audience carpet. So there wasn't anybody here. When I came back down from the dome, then the carpet field got excited and there's 60, 70 people in here. Oh, I shouldn't say that out loud. Edit that from the video. So when you add a little energy to a field, you get something out of it that you can call a particle or you can call a wave. This is a really cool picture. This shows light that is being a particle and wave at the same time. This came out last year in the Journal of Nature Communications, and they caught light in the process of being both a particle and a wave at the same time. It's kind of neat.
Does that have to do with Einstein's relativity theory?
No, this is quantum theory. So you're dealing with quantum mechanics at this point. Now he did shed light on...
because it's either, it's all energy, but it's relative to your perspective.
It is. You get the observation of what you're seeing. Yeah. And here they're being very careful to observe particles and waves at the same time. Yes?
Yeah, my comment, the cosmological constant going back
Yeah.
light. Actually, Einstein considered that the biggest mistake he ever made.
Correct.
Because he postulated it, his peers talked him out of it, and now we're reconsidering.
All right. Well, he used it, his preconceived idea of the universe was that it was unchanging. It wasn't expanding and contracting. General relativity said, hey, it should be either getting bigger or getting smaller. So he put a cosmological constant, a fudge factor, in there to fix the things to make the universe stay steady. And then Hubble came along and said, uh-oh, all the galaxies are rushing away from us like we hadn't had a shower. And so the universe was expanding, and he went, okay, that was a blunder. His constant is back, and it has use, actually. So, yep. All right, so let's talk about fields. Magnetic field is probably the easiest one to visualize. You have a south pole and a north pole and a magnet, and if you sprinkle little metal filings around it, you get a picture of the magnetic field. That's kind of pretty, and you get three-dimensional pictures of the Earth's magnetic field doing like this. Gravity, though, is sort of like a field, but you only have the south pole side. Everything is coming into gravity, and unless the cosmological constant, or the dark energy, is some anti-gravity force, which isn't in favor, then there is no other side but the south to gravity. The strong nuclear force also just pulls in. The weak nuclear force can push or pull. And so it's responsible for radioactivity, helping nudge particles out of the nucleus of an atom. So that's a field, though. And I'm going to break these fields into 3 categories. You've got matter. Everybody's used to that. Electrons and its siblings, quarks, protons, neutrons, all the stuff that makes life and chocolate chip cookies good is matter. So there's fields for all these. You can consider a field approach to how these work. Forces I've already talked about. You have photons. The weak nuclear force have W and Z bosons, and those aren't clowns. So no clown sightings in the subatomic thing here. Gluons, that's the strong nuclear force that holds the nucleus of an atom together. And then gravitational force. And then a new special one, the Higgs phenomenon. We're going to talk about Higgs in just a bit. And like I said before, some particles like to talk to some forces, some don't like to. Photons don't care about the weak nuclear force or the strong, but photons do care about electromagnetism and gravity. So I'm not going to get any more into it than that some particles work with some forces and some don't. Thing to remember is that there really is no matter here. There's no solid material to any of these oscillations. A field is a field is a field. You're just a bunch of fields. Sorry. I've said you're a bunch of empty space, now I said you're a bunch of fields. I'm insulting my audience without ending. So the recipe is, you take some vacuum, you add some energy, and you can get stuff. That's kind of nice. If you put enough energy into empty space, you get particles to appear. If you take 2 ordinary protons, like in the Large Hadron Collider, CERN, smash them together at high energies, that's a vacuum, the best vacuum they can get inside the beamline of the device. All you're doing is smashing these 2 little particles together. You get a whole zoo of other particles out of it. They weren't hiding in the proton. They were created out of the nothing with that explosion. So that brings us to the Higgs. It was suspected to exist, this Higgs particle, this Higgs field, in the 1960s. It was finally announced, coming from CERN, the 4th of July, 2012. I was camping up at Red Feather Lakes, and I saw it pop up when my phone got a little bit of edge network, and I went, the Higgs, the Higgs, the Higgs! And everybody at the campsite was, what are you doing? So we got Nobel Prizes that went around for that. And what the Higgs does, I'm going to explain this in a way that everybody's going to get, is, we'll start with this. It's easy to write physics in which all the particles travel at the speed of light. If you saw the original Ghostbusters near the end, they're all going to try to conquer Zool, and he's been warned not to cross the streams because all your particles, your body will explode at the speed of light. And Vinkman said, that's a good safety tip, so don't do that. I know, I butchered the quote. Edit that out too. So it's easy to do that, and maybe that's what physics would be. It is not easy to explain why things can go slower than the speed of light or sit still like this. It's hard to explain that. The Higgs does allow us to explain how things can go slower all the way down to a 0 velocity. Higgs field fills the entire universe, all of the emptiness. There's a Higgs field under it all, and has existed since shortly after the Big Bang. So imagine a field that permeates the entire universe. Every particle feels a field, but is affected in different amounts. So this field that froze out of the Big Bang allows subatomic structures to exist. It allows empty space to sit at a lower energy than any old normal empty space would. And when it needs to, the Higgs field or Higgs particles can emerge from nothing and do their job. So what is their job? All right, so here's a crowd over here. And if you are like me and not an international celebrity of any kind, if you wanted to walk from here to here, you can just walk right through, find kind of a nice easy path and make it through. No problem. All right, now if you're in Denver and one of the Denver newscasters comes and tries to walk through here, they'll probably not have too hard of a time. Maybe this person here will go, hey, aren't you the lady who does the weather? And she, oh, can I have your autograph? And she stops for a moment, gives an autograph, and walks on through. All right, now let's say that Tom Cruise comes here and tries to walk through. People go, oh, hey, it's Tom Cruise, Tom Cruise. And the crowd starts to kind of bunch around the celebrity. I need an autograph, I need to go. And Tom Cruise is going to have a hard time making it through this crowd with any speed at all. Now let's say a president or the Queen tries to make it through, and now you've got Secret Service, and they're all over the place, or the guard is, and there's people taking pictures, and the phones are up, and it'd be a bad idea to try to get through it all. They're going to bring the president or a queen to a stop in this crowd. So that's what the Higgs particles do. And the particles that interact with the Higgs field get slowed down by this interaction of particles popping up around them. The W and Z weak force bosons really feel it, but everything else does to some. So the more strongly a particle interacts with the Higgs field, the heavier it is. That's where particles get mass. Things like protons and neutrons get most of their mass from the binding force holding them together. The photon and maybe the graviton are the only particles that get to sail through at full speed, at the speed of light, not getting slowed down at all. So we've got gravity. Einstein had stuff to say about gravity, like the graviton. General relativity shows that where you have lots of mass, from the Higgs field, you have lots of gravity. Gravity bends space itself, or space-time, as Einstein worked it out. You have a field, a gravitational field that fills the universe, curving space and time. The more mass you have, the more gravity. Space compresses in the downward direction towards a planet, a star, or a black hole. And time slows down as you get into stronger and stronger gravity wells. Space adapts to the matter and energy in it, and then gravitation and matter and energy adapts to the curvature of space as it tries to travel around. The force particle this time is the graviton, and we haven't seen these yet. They're going to be incredibly hard to see, especially if they are massless, which isn't that kind of confusing. The particle of gravity, it doesn't have mass, but anyways, have you seen the graviton? Not yet, but it may not be far away. Okay. Yes?
If the Higgs boson embodies mass to usins in field interactions, mass is required for gravity. How does the Higgs boson play into explaining gravity? Because obviously the Higgs has to be there, whether it's the Higgs boson or the Higgs field.
Right.
To embody mass to something.
Correct.
Mass is required for gravity.
Correct.
How does that feed into explaining gravity with the graviton of a spin of 2, which we can't explain?
Yeah, I think you're beyond where I can push tonight. Yep.
Burning question.
It's a big question. Yep.
Yes. It's got to play with each other.
Yep, and I think there's a Nobel waiting for that.
Thanks.
You can do it, you can do it. So what's really neat is, well, we talked about waves, right? We have gravity waves. Einstein said we should, and we do. In 2014, 2015, LIGO, I don't know how you pronounce LIGO, is an observatory that used a very similar experiment to Michelson and Morley's to see black holes merging across the universe. We could see the gravitational waves as the two came together into one black hole. So this is now proven, and I'm sure there's Nobel Prizes coming from that. All right, but we got even more in nothing than that, because we have vacuum energy. What are you talking about? It was first postulated in the 30s, also called zero-point energy. How many people like watching Stargate? All right, so this is a ZPM, zero-point module. This is what powered everything. It's a great, we're going to talk about the power that could be in something like this in just a moment. I've heard they might revive it, but it might ignore all the canon from the TV show, but I'd be sad. Anyways, it all comes down to uncertainty. So there's Heisenberg with his good scientist hair. And he said that if you have things like position momentum, two measurable quantities of a particle that relate to each other, or energy and time, you can only know one and not so much the other. So this is a tough sentence. You can't not have anything at all going on below the level of certainty. It's another double negative, but I'll explain it with this picture. So let's say you know that all the particles in the universe go left to right the way you read a book. So here's a little particle, and you know presently where it is, very accurately. You know that things go left to right in our experiment, so in the next second, minute, hour, it's going to be maybe up here, over here, over here, over here. I don't know where, just someplace in half of this picture. So we don't know the future position of this particle. Okay, here's one moving. If I say this moves that far in a minute, great. So where is it right now? I'm not too sure. I'm kind of fuzzy on it. But where is it going to be in a minute? Oh, probably right about here.
I think it might be in the middle.
Might be over here? Oh, yeah, it's close. It's most likely in the middle, yep. But it could be here. It could be here. That's the whole idea of quantum mechanics. So you just discovered quantum mechanics. Nobel, right here. So down here in empty space, below where you can make any reliable measurements, we have virtual particles coming apart. There's an electron. There's an anti-electron, antimatter particle. They pop apart out of nothing, go whee! They travel for a moment, and before anybody can make a measurement of them, they re-annihilate each other. And this is happening throughout all of the empty space universe because of Heisenberg's uncertainty principle. And you say, well, John, that seems crazy. Surely you can't measure that. Yes, you can. You can do it in the lab, actually. You get a big apparatus, pump all the air out, get the best vacuum you can, and you put two extremely precise plates really close together. And what happens is that these little particles are coming and going, coming and going, coming and going, killing each other, coming out, killing each other, coming out, killing each other in every possible direction. When these plates are really close, now there isn't room for the side-to-side particles to come apart and rejoin, come apart, rejoin. So you have less of these little virtual particles happening, so you get a push inward from the outside. It's called the Casimir effect. That's the scientist who discovered it. And if you want, but John, you don't want to talk about particles. You talked about quantum field theory. Okay, we can do waves too. So if we have waves, the little bitty waves fit between the plates, but the big waves don't. So because you have big waves on the outside, but no big waves on the inside, they push together. These virtual particle wave effects still push it together the same amount. Just a different bunch of mathematics to get the Casimir effect. Stephen Hawking became famous by getting Hawking radiation named after him. I don't think he named it himself. Saying that these little particles happening in space, great. Sometimes they may fall into a black hole. So this gray area is a black hole stretched out in time. And so what? Fall into the black hole, all gone. Or if they pop out and they re-meet over here, who cares? But once in a while, one's going to go in, and the other virtual particle is going to stay on the outside. Oh no, where'd you go? And there's another one, and there's one going in. And so what you get is an overall loss of energy in the black hole, and you have what looks like a glow, a temperature for a black hole. Now the universe is way too hot right now. John, it's only 2.7 degrees above absolute zero. That's way too hot for most black holes of stellar size or bigger to be even close to actually evaporating now. They're still growing, eating up black body radiation from the Big Bang. But someday the universe will cool enough, the black holes will stop growing from that and will eventually shrink and maybe pop. We don't really know. We need a quantum theory of gravity to figure the end out. Even inside atoms, these little virtual particles are important. So here's an electron coming close, here's an electron coming close. They exchange a virtual photon and go, ah, and they bounce off each other. Remember, electrons don't have any size that we know of. They just get close, exchange a little thing and bounce off. The surface of all your atoms are electrons. So the surface of you are all electrons. I put my hand together and push. Oh, I can't get through the electrons. My electrons are pushing against each other. It's all electrons. All I'm seeing of you is a shell of electrons. The pressure you're feeling from the chair below you is electrons. And they're right now exchanging quadrillions of virtual photons to keep you from falling into the earth and vanishing. All right, so let's go back to the 0-point energy of these little particles. How much energy is available? If there's an estimate, if you get a venti cold from Starbucks, 30 ounces, you might have enough 0-point energy to boil off the Pacific Ocean in 1 second. That's why that module will be able to power a wormhole and get you over to Teal'c's home planet. But other estimates are vastly smaller, and there's actually a break in our understanding of how quantum mechanics scales up to the universe. It's illustrated here, that needs to be solved by somebody. So get on it right now. So that's all the stuff that is in empty space, but maybe empty space itself doesn't exist. So we're going to look really briefly at how quantum mechanics and relativity hint at maybe space doesn't even exist in a real way. So here is something called entanglement. Entanglement is a neat little quantum effect that if I have an atom and I get things just right in my experiment, that I beam it with light and 2 photons pop out, that I know one is going to be wiggling up and down this way, one's going to be wiggling this way. I can let them go across the universe. If nothing interferes with them, I can go over here, measure my photon, and go, oh, it's going up and down. I know that the one on the other side of the galaxy over there is going side to side. And so what, John? Okay, well, what if I decide to measure the side to side instead? And I find it side to side. Ah, now I know the other side of the universe, or galaxy, whatever, is up and down. Or what if I decide to measure its circular polarity instead? Okay, I'm going to do that. Okay, now I know the one way over there has the opposite. So you can't use it for communication. If you have your experimenter over there going, oh, we just measured it this way, they must have done it that way. You don't know until you send an email all the way back to your first person to say, what did you do? But there's all sorts of neat things with teleportation and like that you can do with subatomic particles. Yes, you're in that area. I'm not going to get into the kitty tonight, but yep. Einstein didn't like it so much that he penned a paper with a few other scientists and called it spooky action at a distance, but we do this now regularly in the lab. So we know that this phenomena happens. But I just said all that stuff. So in a way, the gap between these two little particles, the intervening space doesn't matter. Now you say, well, maybe there's some hidden secret wiring behind the universe that lets these talk to each other faster than the speed of light. Well, this very smart guy came up with this complex experiment or thought process that's now been turned into an experiment called Bell's inequalities, showing that no, there is no hidden physics here. This is how these subatomic particles work. They work as if they're still completely related to each other without anything being connected in between, as if there is no space between them. That's as deep as I want to go on that. Let's go to relativity now and look at the same. If you travel at a good fraction of the speed of light, the stars around you will look closer. Time is slowing. If you're going around a black hole, the closer you get to the black hole, the more distant the universe will appear to every experiment you can come up with. If you go on this side of a black hole and your friend goes to the other side of the black hole, and you want to know the distance between the two of you on a straight line, it's infinite, an infinite distance. To a photon traveling at the speed of light, it springs free from the photosphere of the sun, instantly traveling the speed of light. Time stops for it, and until it hits your arm when you're walking outside in the afternoon, then it goes, whee, I'm here. It went from the surface of the sun to you with no intervening space that it saw. So these are reference frames ideas, but again, with time and space malleable, space isn't quite as real as our intuition tells us. It's disturbing that you can look at these two successful theories, quantum mechanics and relativity, and even explain away empty space. But for nothing that may be nothing, that's something, and I have nothing else to say.